Welcome! Today, we'll be tackling LeetCode problem number 537, complex number multiplication. This problem will challenge our ability to parse and manipulate complex numbers represented as strings. Let's dive in to explore the solution step by step. In this problem, we are tasked with multiplying two complex numbers. These numbers are provided as strings, formatted as a plus by, where a represents the real part and b represents the imaginary part of the complex number. The letter I here denotes the imaginary unit, which satisfies the property that I squared equals -1. For example, the string 1 plus 1i corresponds to the complex number 1 plus I, and 3 plus -2i corresponds to the complex number 3 minus 2i. Your goal is to write a function that takes two such strings as input, computes their product, and returns the result as a string in the same a plus by format. The output of the function should be a single string that represents the product of the two input complex numbers, formatted as a plus by. To better understand how the multiplication works, let's walk through an example. If the input strings are 1 plus 1i and 1 plus 1i, they represent the complex numbers 1 plus I and 1 plus I. The product of these two numbers can be calculated as follows. For the real part, we compute 1 times 1 minus 1 times 1, which gives us 0. For the imaginary part, we compute 1 times 1 plus 1 times 1, which results in 2. Combining these, the product is 0 plus 2i, represented as the string 0 plus 2i. So, the result of multiplying 1 plus 1i by 1 plus 1i is 0 plus 2i. Now, let's consider another example to further clarify this process. Suppose the inputs are 1 plus -1i and 1 plus -1i. These represent the complex numbers 1 minus I and 1 minus I. For the real part of the product, we calculate 1 times 1 minus -1 times -1, which evaluates to 0. For the imaginary part, we compute 1 times -1 plus -1 times 1, which gives us -2. Putting these together, the result is 0 minus 2i, represented as the string 0 plus -2i. Now let's look at a slightly more complex example. If the inputs are 3 plus 2i and 1 plus -4i, these correspond to the complex numbers 3 plus 2i and 1 minus 4i. For the real part, we calculate 3 times 1 minus 2 times -4, which simplifies to 3 plus 8, giving us 11. For the imaginary part, we compute 3 times -4 plus 2 times 1, which results in -12 plus 2, or -10. Combining these, the product is 11 minus 10i, represented as the string 11 plus -10i. The problem also comes with a set of constraints and edge cases that your solution must handle. The integers a and b in the input strings lie within the range of -100 to 100. The output string must strictly follow the a plus by format. Some edge cases to consider include inputs where both numbers have only real parts, such as 2 plus 0i and 3 plus 0i, or cases where both have only imaginary parts, like 0 plus 2i and 0 plus 3i. You should also handle inputs where one or both coefficients are negative, such as -1 plus -1i and 2 plus -3i. Your solution must correctly account for all these scenarios. When tackling the problem of complex number multiplication, one of the biggest challenges involves parsing and handling the input strings, which represent the complex numbers, and then correctly applying the rules of complex arithmetic. Let's consider the brute force approach as an initial strategy. The intuition here is straightforward. We extract the real and imaginary parts from the given string inputs and compute the product directly using the formula for multiplying two complex numbers. Specifically, if we have two complex numbers, a plus by, and c plus d, their product is calculated as a seed bd, for the real part and add plus bc, for the imaginary part. To achieve this, the steps involve parsing the strings to extract the integers a, b, c, and d, performing the arithmetic calculations for the real and imaginary parts, and then combining these results into the required output format. This approach has a time complexity of O(n), where n is the length of the string, due to the parsing step. While this method is simple and leverages the mathematical properties of complex numbers, it does come with a trade-off. Manual parsing can be error-prone, especially when considering edge cases in the input format. Now, let's refine our approach by using Python's built-in string manipulation functions to simplify the parsing process. Instead of manually extracting the components of the input strings, we can use methods like split to streamline the task. First, we use split plus to separate the real part from the imaginary part of the string. Then, we split the imaginary part further using split I to isolate the numeric value. Once these components are extracted and converted to integers, we can compute the product using the same multiplication formula as before. After the calculations, the result is formatted back into the required real plus imaginary *I format. This approach has the same O(n) complexity as the brute force method since parsing still depends on the input string length. However, by leveraging built-in functions, we reduce the likelihood of manual parsing errors. The trade-off here is that the approach assumes the input will strictly follow the A+by format. If the input deviates from this structure, additional error handling will be necessary to ensure robustness. For this problem, we decided to go with the optimized approach that uses Python's built-in functions. This strategy strikes a balance between simplicity, clarity, and reducing the chances of errors during implementation. By utilizing Python string operations such as split, we avoid the complexities and risks associated with manual string manipulation. The key insight here is that once the input is parsed correctly, the rest of the problem becomes trivial arithmetic. This realization underscores the importance of focusing on accurate and efficient parsing. The formula for complex number multiplication is straightforward, and the arithmetic calculations are simple once the integers are extracted. We chose this approach not only for its efficiency, since both methods are O(n), but also for its ability to simplify the implementation. Error reduction is another significant advantage, as built-in functions tend to handle common edge cases more gracefully. Additionally, the implementation is cleaner, making the code easier to read, debug, and maintain. Finally, it's important to consider the trade-offs of the chosen approach. While the optimized method is robust and efficient for well-formatted input, it does require additional validation to handle cases where the input deviates from the expected A+by structure, such as missing the plus or I characters. On the other hand, the brute force approach provides greater control over the parsing process, but this comes at the cost of increased complexity and a higher likelihood of bugs, particularly when dealing with edge cases. In conclusion, the optimized approach offers the best balance between simplicity, clarity, and performance for this problem. It enables us to write concise and maintainable code while minimizing the risk of parsing errors. By prioritizing these factors, we ensure a solution that is not only efficient but also easier to adapt and debug if necessary. To solve this problem, we need to multiply two complex numbers provided as strings and return the result in the same string format. Each input string is structured as A+by, where A represents the real part, B represents the imaginary part, and I is the imaginary unit. The key to solving this lies in understanding the arithmetic of complex numbers. When multiplying two complex numbers, we use the formula A+by C plus D equals AC BD plus AD plus BC I. Here, the real part is calculated as AC BD, while the imaginary part is calculated as AD plus BC. Additionally, since I** equals -1, the imaginary unit plays a crucial role in simplifying the arithmetic. Another important step is extracting the real and imaginary parts from the input strings. This involves parsing the strings by splitting them into components and converting these components into integers for arithmetic operations. Efficiently performing these calculations ensures the solution is both correct and optimized. So, the first step in the algorithm is to parse the inputs by separating the real and imaginary parts and preparing them for multiplication. Now that the inputs are parsed, the next step is to multiply the components of the complex numbers. Using the formula introduced earlier, we calculate the real part of the product as A*C, B*D. Similarly, the imaginary part is calculated as A*D plus B*C. Once we have these two components, we need to format the result back into the required string format. This is achieved by combining the real and imaginary parts into a string like real_part plus imaginary_party. It's also critical to handle edge cases, such as when one or both complex numbers have zero real or imaginary parts. For instance, if the input is 0 plus 0i, the output must also be in the correct format. Additionally, we assume that all input strings follow the A+by format consistently, with no spaces or unexpected characters. From a data structure perspective, strings are used to hold the input and output values, while integers are employed for precise arithmetic calculations, avoiding the potential pitfalls of floating point errors. The implementation of this algorithm is straightforward. We first parse the input strings by removing the trailing I and splitting the strings into the real and imaginary parts. These parts are then converted into integers to perform the calculations. After parsing, the real part of the product is calculated using the formula A*C, B*D, and the imaginary part is calculated as A*D plus B*C. Finally, we use Python's f-strings to format the result into the required string form, combining the real and imaginary parts with the I at the end. For example, given the inputs 1 plus 1i and 1 plus 1i, the function outputs 0 plus 2i. This is achieved by following the exact same parsing, arithmetic, and formatting steps. Parsing ensures we isolate the components accurately, while using integer arithmetic guarantees precise results. Additionally, formatting the final string is straightforward and ensures adherence to the expected output structure. When formatting the result, Python's f-strings make it easy to combine the real and imaginary parts into the desired output format. Now let's analyze the algorithm's complexity. For time complexity, all parsing and arithmetic operations occur in constant time since the input strings have a fixed length. This gives us a time complexity of O(1). Space complexity is also O(1), because only a few integer variables are used for calculations, and no additional data structures are required. It's important to consider edge cases. For example, inputs like 0 plus 0i must return 0 plus 0i, even when all components are zeros. Negative values, such as -1 plus 2i, are also handled seamlessly by the algorithm. Multiplying a complex number by itself, like 1 plus 1i squared, should yield the correct result. Lastly, Python's support for arbitrary precision integers ensures that even with large values, there's no risk of overflow. With these considerations, the solution handles all possible scenarios effectively. Let's walk through an example to solidify our understanding. Suppose the inputs are number 1 equals 1 plus 1i and number 2 equals 1 plus 1i. First, we parse number 1, extracting a equals 1 and b equals 1. Similarly, for number 2, we extract c equals 1 and d equals 1. Next, we calculate the real part of the product as 1 by 1, 1 by 1, which equals 0. The imaginary part is calculated as 1 by 1 plus 1 by 1, which equals 2. Finally, we format these results into the string 0 plus 2i. Therefore, the output for this example is 0 plus 2i. This step-by-step process highlights how parsing, arithmetic, and formatting come together to produce the correct result efficiently and accurately. This Python solution efficiently solves the problem of multiplying two complex numbers represented as strings. The method complex number multiply takes two string inputs, number 1 and number 2, each of the format a plus by, where a and b are integers. The first step is to split the input strings into their real, a, c, and imaginary, b, d, components. To do this, the :1 slicing removes the trailing I, and the split plus method separates the real and imaginary parts. The map int function then converts these parts into integers for calculation. Next, the multiplication formula for complex numbers is applied: a plus by asterisk c plus d equals ac bd plus add plus bc I. The real underscore part is calculated as a asterisk c b asterisk d, and the imaginary underscore part is a asterisk d plus b asterisk c. Finally, the result is formatted as a string in the required format real plus imaginary I using Python's f-string formatting, and returned as the output. This implementation ensures clarity and handles all edge cases, such as negative real or imaginary parts, by leveraging Python's built-in arithmetic and string manipulation capabilities. The solution is both concise and efficient, with a time complexity of O(1), since all operations are constant-time arithmetic and string manipulations. This is the Java implementation of LeetCode problem number 537, complex number multiplication. It mirrors the logic of the provided Python solution, converting input strings into real and imaginary components, performing the multiplication using the formula, and returning the result as a formatted string. Key differences include Java-specific string handling, e.g., split and substring, and explicit type declarations for variables. The implementation adheres to Java conventions, ensuring readability and consistency. Let's start with the first example where both complex numbers are 1 plus 1i. The first step is to parse the inputs. By removing the trailing I, we get 1 plus 1 for both numbers. Splitting this string at the plus sign, we extract the real part as 1 and the imaginary part as 1 for both number 1 and number 2. Next, we apply the formula for multiplying complex numbers. The real part is calculated as the product of the real parts minus the product of the imaginary parts, 1 times 1 minus 1 times 1, which gives us 0. For the imaginary part, we calculate the sum of the cross products, 1 times 1 plus 1 times 1, which results in 2. Finally, we combine these components into the string 0 plus 2i, which is our result for this example. Now, in the second example, the complex numbers are 1 plus -1i. As before, we start by removing the trailing I, leaving us with 1 plus -1. Splitting this string, we determine that for both numbers, the real part is 1 and the imaginary part is -1. Using the formula, the real part is calculated as 1 times 1 minus -1 times -1. This simplifies to 1 minus 1, which equals 0. For the imaginary part, we compute 1 times -1 plus -1 times 1. This results in -1 minus 1, giving us -2. Combining these, we form the result as 0 plus -2i, which can also be written as 0-2i. This is the output for the second example. In the third example, we work with the complex numbers 3 plus 2i and 1 plus -4i. Removing the trailing I, we are left with 3 plus 2 and 1 plus -4. For number 1, the real part is 3 and the imaginary part is 2. For number 2, the real part is 1 and the imaginary part is -4. Using the formula, we calculate the real part as 3 times 1 minus 2 times -4. This simplifies to 3 plus 8, giving us 11. For the imaginary part, we compute 3 times -4 plus 2 times 1. This becomes -12 plus 2, which equals -10. Combining these, we get the result as 11 plus -10i, or equivalently, 11-10i. This is the output for the final example. To analyze the time complexity of our solution, we start with the first step, parsing the input strings. The input strings, number 1 and number 2, are split into their real and imaginary components by using the split plus method, and we also slice off the last character to remove the trailing I. Since splitting requires scanning the entire string and the length of the strings is n, this operation takes n time for each input. Once we have the substrings, we use map int to convert the parts into integers. Because the integers are small and bounded by the input constraints, this conversion is a constant time operation, O(1). Combining these steps for both input strings, the total cost for parsing is O(n) plus O(n), which simplifies to O(n). Next, we perform the actual complex number multiplication. Using the formula, we compute 4 products and 2 additional operations, subtraction and addition. Each of these arithmetic operations is constant time, O(1), as we are working with fixed-size integers. Hence, the total cost of the multiplication is also O(1). Now, after computing the multiplication, we need to format the output as a string. This involves converting the integer results of the real and imaginary parts into strings and concatenating them with the appropriate format, such as f, real_part, plus, imaginary_part, I. Since the numbers involved are bounded by the problem constraints, this is a constant time operation, O(1). When we combine all these steps, the overall time complexity becomes the sum of parsing, which is O(n), the multiplication, which is O(1), and the formatting, also O(1). Since O(n) dominates, the total time complexity of the solution is O(n), where n is the length of the input strings. Turning to space complexity, we first consider the input storage. The input strings, number 1 and number 2, are passed as arguments, meaning no additional memory is required for them. Next, we look at the intermediate variables. The real and imaginary parts of the numbers a, b, c, and d are stored as integers. Each integer takes a constant amount of space, O(1), resulting in a total of O(1) space for these variables. Similarly, the intermediate results of the multiplication, real_part and imaginary_part, also occupy constant space, contributing another O(1). Finally, the output is constructed as a new string, and while its length depends on the magnitude of the numbers, it remains bounded by the constraints. Therefore, the space used for the output is also O1. In conclusion, the overall space complexity of the solution is O1, because no data structures are used that scale with the size of the input. All intermediate variables and the output string occupy constant space. This efficiency is worth noting because a less optimal approach, such as manually parsing the input or using arrays to store intermediate results, could increase both time and space complexity. For example, such approaches might involve additional memory usage of O(n) or more for storing intermediate data. In this solution, however, the parsing step determines the runtime, leading to a time complexity of O(n), while the constant space usage ensures the space complexity remains O1. This makes the solution not only mathematically sound but also optimal and straightforward for solving the problem of multiplying two complex numbers represented as strings. When solving this problem, there are several common mistakes to watch out for. First, incorrect parsing of complex number strings can lead to issues, especially when handling edge cases like 1 plus 0i versus 0 plus 1i. To avoid this, ensure you use robust string splitting and parsing techniques to reliably extract both the real and imaginary components. Next, sign errors during multiplication are another frequent mistake. It's essential to remember that the product of two imaginary units, I times I, equals -1. Carefully applying the formula, which is a plus by asterisk c plus d equals ac bd plus add plus bc I, will help prevent these errors. Another pitfall is mixing integer and string outputs. For example, returning the result as a tuple or list instead of the required string format x plus e. To fix this, format your result as a string using concatenation or formatting functions like Python fstrings. Finally, overlooking negative numbers can cause incorrect results if the real or imaginary parts are negative. Incorporating test cases with negative components during validation is a great way to catch these issues early. Another mistake to avoid is inefficient parsing or operations. Overcomplicating your parsing logic with nested loops or redundant steps can slow down execution. Instead, utilize efficient string manipulation functions like split and replace to streamline the process. Now, from an interview perspective, this problem is an excellent opportunity to showcase your ability to handle non-standard input formats and apply basic algebraic operations. Parsing and string manipulation are key skills here. While the problem has a fixed input size, making it inherently O1, interviewers might ask how you generalize your approach for larger datasets or handle multiple inputs. It's also important to discuss edge cases like 0 plus 0i, 1 plus 0i, and -1-1i, as being aware of these demonstrates attention to detail. Additionally, follow-up questions may include extending your solution to support operations like division of complex numbers or handling invalid inputs gracefully, so be ready to discuss those possibilities. This problem is closely related to a few others on LeetCode that can help reinforce the underlying concepts. For example, LeetCode 49, Group Anagrams, focuses on string manipulation and hashing, which ties into efficiently parsing and handling string data. LeetCode 43, Multiply Strings, is another great comparison, as it requires careful parsing and implementing multiplication without directly relying on numeric types. Similarly, LeetCode 67, Add Binary, emphasizes string-based arithmetic and highlights the importance of handling edge cases for non-standard inputs. Finally, LeetCode 415, Add Strings, is highly relevant as it reinforces string manipulation and arithmetic logic for custom formats. Each of these problems can provide additional practice and insight into the skills needed for solving complex number multiplication. There are also alternative approaches you might consider when tackling this problem. One option is using regular expressions to extract the real and imaginary components directly from the input string. This approach is concise and efficient, but it can be harder to debug if you're not familiar with regex. Another method is manual parsing with index tracking, where you process the string character by character to extract the components. While this approach avoids relying on additional libraries, it can be slower and more prone to errors. Finally, you could use built-in complex number libraries, such as Python's complex type, to simplify the implementation. This allows you to convert the input strings into complex numbers and operate on them directly. However, this method may not be allowed in interviews, where the focus is often on demonstrating manual calculations. Each of these methods comes with trade-offs, so choose the one that best fits your scenario or aligns with the constraints of the problem. Great job! To recap, we broke down the problem by parsing the complex numbers, applied the multiplication formula, and ensured our solution was efficient. Remember, practicing such problems strengthens your problem-solving and debugging skills. Thanks for watching, and see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!